Welcome to section 3.6, graphing rational functions. All right, objective number 1. Graph a rational function. Okay, so in our first example here, we're asked to graph the rational function r of x equals x minus 1 divided by x squared minus 9. Okay, so for step number 1, we're asked to factor the numerator and denominator of r and then find the domain of the rational function. So let's take our function r of x, which is x minus 1 over x squared minus 9. And we want to factor the numerator and denominator. So the numerator is already in factored form. The denominator, however, is a difference of squares. So we can rewrite that as x minus 3 times x plus 3. Okay. All right, and so now we have our function r of x in factored form. So the next step here the next part in this step is to find the domain of the rational function. So the domain of the rational function is going to be all real numbers except for the x values that make the denominator 0. So our denominator is 2 factors. So we're going to set both factors equal to 0 and then solve for x. So x equals 3 and x equals negative 3. So our domain is going to be all real numbers except for when x equals negative 3 and x equals 3. Okay. All right. Now we want to write r in lowest terms. Okay. So our factored form of r of x came out to be x minus 1 divided by x minus 3, x plus 3. Okay. Now, if we were able to simplify r of x, we would have a common factor in the numerator and a common factor in the denominator to cancel out. Since we do not, r of x is already in lowest terms. Okay, so r of x is already in lowest terms. All right. Okay, so let's go to step 3. Find and plot the intercepts of the graph. Use multiplicity to determine the behavior of the graph of r at each x-intercept. So we want to find the intercepts, so that means we want to find the x and the y-intercepts. So let's first find our y-intercept. Okay, now to find the y-intercept, we know that x is 0. So if we substitute x into our rational function, we would get 0 minus 1 divided by 0 squared minus 9, which equals 1 over 9. Okay, so this would give us the ordered pair 0, 1 ninth. Okay. Now for the x-intercept, we are going to set r of x equal to 0. Okay, so when we set r of x equal to 0, we have 0 equals x minus 1 divided by x squared minus 9. So if we multiply both sides by x squared minus 9, we will then have 0 equals x minus 1, which then gives us x equal to 1. This then gives us the ordered pair 1, 0. Okay. Now, the multiplicity of this x-intercept, all right, the multiplicity is going to be 1, right? Because the factor that gave us x equals 1 has a power of 1, okay? So this has, so let's say the multiplicity of 1 is odd. And since it is odd, the graph crosses the x-axis at x equals 1. Okay, so that's the behavior of the multiplicity on our graph. Okay, and we have our x-intercept and our y-intercept. All right. So now we want to find the vertical asymptotes. So we're going to graph each vertical asymptote using a dashed line and then determine the behavior of the graph on either side of each vertical asymptote. Okay, so remember the vertical asymptotes are the real zeros of the denominator. And so when we factored r of x, our function, we got x minus 1 over x minus 3 times x plus 3. So if we set our denominators equal to 0, we then get x equals 3 and x equals negative 3. So these would both be our vertical asymptotes. Okay. All right. So the multiplicity of the zeros, all right, so the multiplicity of both of these zeros give rise to the vertical asymptotes are both odd. So if we look at their factors, we see here that their powers are 1, so they have an odd multiplicity. So since there's an odd multiplicity, we know then that the graph approaches infinity on one side and then negative infinity on the other. Okay, so let's write that out. So the multiplicity of the zeros that give rise to the vertical asymptotes, which I'm abbreviating VA, are both odd. Thus, the graph approaches infinity on one side and negative infinity on the other. Okay, so that is the behavior of our graph in relation to our vertical asymptotes. Okay, so for step 3, we found our y-intercept and our x-intercepts, noting that the y-intercept is the 0.01 over 9, 1/9. And then we found our x-intercepts, which are the real zeros of the numerator. Okay, and the 0 came out to be 1. And then from the x-intercept, we were able to determine the behavior of the graph at that x-intercept. And since the factor of that 0 has an odd power, it has a multiplicity of 1, the graph crosses the x-axis at that point. And then for step 4, we found our vertical asymptotes, which are the real zeros of the denominator. And we then identified the multiplicities that got our real zeros of the denominator, which both came out to be odd as well. So we know then that the graph is going to approach infinity on one side and negative infinity on the other. Okay. So for step 5, we're now going to find the horizontal or oblique asymptote if one exists. And then we'll use that information to graph the asymptote using a dashed line, and then find points, if any, where the graph of R intersects the asymptote, and then plot the points. Okay. So our function is R of x equals x minus 1 divided by x squared minus 9. So to determine whether we have an oblique or horizontal asymptote, we need to find the degree of p of x, which is the polynomial in the numerator. And this has a degree of 1. And then find the degree of the polynomial in the denominator. And this has a degree of 2. So that means n equals 1 and m equals 2. So n is less than m. Since n is less than m, our horizontal asymptote, which I abbreviated HA, is going to be y equals 0, which is our x-axis. Okay. So now we want to determine if there is a point on the graph that intersects with this asymptote. Okay. And so to find that, we're going to set y equal to 0 and identify the x value for this point. So r of x equals 0 is similar to us finding the x-intercept. And when we found that in the previous step, I believe it was step number 3, we got x equals 1. So that means the graph intersects the horizontal asymptote at 1, 0. Okay, awesome. Now for step number 6, we're going to use the real zeros of the numerator and denominator of R to divide the x-axis into intervals, and then determine where the graph of R is above or below the x-axis by choosing a number in each interval and evaluating R, and then plot those points that we find. So the real zeros that we have identified thus far in steps 1 through 5 are going to be 1, 3, and negative 3. 1 is the real zero of the numerator, and 3 and negative 3 are the zeros of the denominator. So now we have our table here where our axis, x-axis, is divided into 4 intervals. These intervals are divided by our real zeros, which are negative 3, 1, and 3. So our first interval is going to be negative infinity to negative 3. Next would be negative 3 to 1, then 1 to 3, and then 3 to infinity. Now we need to choose a number in each of these intervals. I recommend choosing a number that you don't already know. So for example, in the first interval, I'm going to choose negative 4. In the second interval, I'm going to choose negative 1. In the third interval, I'm going to choose 2. And in the last one, I will choose 4. So we want to find the value of R, which means if I substitute in negative 4, substitute in negative 1, 2, and 4, what would be the y values associated with that. And so for this, we can grab our calculator to help us. So in our calculator, we are going to enter in our equation. So you'll clear whatever equation you previously had there, or you can reset your calculator. We're going to enter in our function. So we'll enter in our equation. So this will be x minus 1 in the numerator, and then x squared minus 9 in the denominator. Enter that in. I'll then go to my table by pressing second graph, and I now have some values here. So I want the y values for my chosen numbers. So I'm going to need -4, which is -5/7, or roughly -0.7. Then I'll need -1, I'll need 2, and I will need 4. Okay. All right. So we're going to take those values and place them on our chart. So I will write them in decimal form, but feel free to write them as a fraction if you prefer. Okay. And I rounded to one to 2 decimals. Now, we want to find the location of the graph of this new point. So my point on the graph in the first interval is -4, -0.7. So since my y is negative, it's going to be below the x-axis. In my second interval, I have the point -1, 0.25. Since my y is positive, it is above the x-axis. In my third interval, I have the point 2 and -0.2. Since my y is negative, this is below the x-axis. And then for my fourth interval, I have the point 4, 0.4, and this is above the x-axis. Okay. So now that I have my points, I can now move on to step number 7 and take all of the results and information that I have collected from steps 1 through 6 and graph R. Okay, so let's graph that. So the first thing that we want to do, and that I recommend, is to plot your asymptotes. So we have a vertical, we have 2 verticals actually, and we have 1 horizontal. Now the 1 horizontal is going to be the x-axis. So that's when y equals 0. Then we also have x equals -3. So this is x equals -3. And x equals 3. So we want to draw those vertical asymptotes. X equals 3. Okay. The next thing that we want to do is plot our points. Okay. So we know we have a y-intercept at 0, 1/9. Okay, 0, 1/9, so that's pretty small. So somewhere in there. All right. And we have a x-intercept at 1, 0. 1, 0. So point right here. Okay. We also have our 3 points that we found in our table. So we have -4, -0.7. Okay, so that'll be like somewhere here. And then we have -1 and 0.25. So that would be somewhere right here. Okay. Then we have 2 and -0.2. So somewhere right here. 2 and -0.2. Then we have 4 and 0.4. So 4 and 0.4. So it's almost 0.5. So that'll be somewhere right here. Okay. Now we also know that for our vertical asymptotes, in step number 4, we identified that because the powers were odd for the factors that gave us these vertical asymptotes, we know the graph is going to be approaching infinity on one side and then approaching negative infinity on the other for both vertical asymptotes. So we know then that our graph will look something like this. So we're approaching negative infinity there. And then we have our graph here. So we'll be approaching infinity up here at the top, negative infinity at the bottom. And then we have something similar here. All right. So at each asymptote, we have a part of the graph going towards infinity and part of the graph going towards negative infinity. Now, to double check this, we can go to our calculator. All right. And we're going to first set up our window to match what we have here on the screen. So we're going to go to, let's see here. So we want to see a little bit past 4 and -4. So let's go to -6. And then our max would be 6. And we're going to go by ones. Our y min will do the same thing. We'll go to -6 and 6, and we'll keep our scale at 1. So now we can press graph. And we see here that we have something very similar to the graph. Note that our graphs here on the right-hand side, it might look like our graph stops, but it actually doesn't. It continues on. The value of our x is very, very small, all right, because it's getting closer and closer to 3, but it never crosses 3, okay? And the same thing down here. And then on the other side, all right, we are approaching -3 in both directions as well. So we see here that our graph is very similar to what we received in the calculator. So we know that the approach that we took is correct. All righty. So in summary, the steps for graphing a rational function. For step number 1, you're going to factor the numerator and denominator of r and find the domain of the rational function. Then for step 2, you're going to want to write r in your lowest terms. For step 3, you will find and plot the intercepts of the graph. So that's going to be your x-intercepts and your y-intercepts. And you're going to use multiplicity to determine the behavior of the graph at r at each x-intercept. Okay. For step 4, you'll find the vertical asymptotes. So you'll graph each vertical asymptote with a dashed line and then determine the behavior of the graph R at each asymptote, whether it's approaching infinity or negative infinity on either side of the asymptote. For step 5, you'll find the horizontal or oblique asymptote if one exists. Remember, there could be cases where neither exists or one or the other. You can never have a graph that has both. Then you'll graph this asymptote using a dashed line as well. And then find points, if any, where the graph of R intersects with the asymptote. So you'll want to plot those points so you can make sure they're represented on your graph. Then step 6, you'll use the real zeros of the numerator and denominator that you've already found to divide your x-axis into intervals. This will help you determine where the graph of R is above or below the x-axis when you choose a number in each interval and evaluate R at that number, and then plot those points. Okay, so you'll have a new set of ordered pairs. And then in step 7, you're going to use all the results that you've obtained in steps 1 through 6 to graph your function of R. All right. So if you're graphing as you go, then you can just check to make sure you have included all of the key information that you found, or you can wait to the end and compile all the information like we did on the previous example in order to graph your function of R. Either way works. All right, let's do another example. Graph of the rational function Rx equals R of x equals x squared minus 4 divided by x. Okay, so we're going to follow those same 7 steps in graphing this rational function. All right, so step number 1 is to factor the numerator and denominator of R. Alrighty. So let's take R of x and let's factor it. So the numerator is the difference of squares, so that would be x minus 2, x plus 2 divided by x. Okay. Next, we need to find the domain. So the domain is going to be all real numbers except for when the denominator is 0. So we set the denominator equal to 0 and we get x equals 0. So our domain is going to be all x values except for when x equals 0. Okay. All right. Step number 2, we need to write R in lowest terms. Looking at our factoring, we do not have any common factors in the numerator and denominator. So R of x is in lowest terms. Okay. And then we go to step number 3. Find and plot the intercepts of the graph and use multiplicity to determine the behavior of the graph at R at each x-intercept. Okay, so to find the y-intercept, we are going to substitute in 0 for x. So we're going to find R of 0. But we just determined in step number 1 that x cannot equal 0. So since x cannot equal 0, there is no y-intercept. So there is no y-intercept since x cannot equal 0. So, no y-intercept since x cannot equal 0. So for the x-intercept, this is when we set r of x equal to 0. Okay, so in other words, we're going to set the numerator equal to 0. So then we can set each factor to 0 and solve for x. And we get x equals 2 and x equals negative 2. So our two x-intercepts are going to be 2, 0 and negative 2, 0. Those are our two intercepts. Okay. Alrighty. Next, for number 4, we're going to find our vertical asymptotes, and then we're going to determine the behavior of the graph of r on either side of the vertical asymptote. Okay, so let's go get some more space here. So number 4, we want to find the vertical asymptote. Okay, now to find vertical asymptote, we're going to find the real zeros of the denominator. And we already know that the real zero of our denominator is going to be when x is 0. So our vertical asymptote is going to be x equals 0. Okay. Now the multiplicity of the factor that got us this vertical asymptote is odd because it's 1. So the graph approaches infinity on one side and negative infinity on the other. Okay. Step number 5, we are locating our horizontal or oblique asymptote if it exists. So p of x is the polynomial in the numerator, and this has a degree of 2. Q of x is the polynomial in the denominator, and that has a degree of 1. Okay, so I notice here that m equals 2 and m equals 1. So between our 4 different types of expressions for the relationship between n and m, n equals m plus 1, meaning 2 equals 1 plus 1. Okay. Now, when n is 1 more than m, we need to find the quotient of this rational expression. So we are going to take x squared minus 4 and divide it by x to find the quotient, which is going to be the equation for our oblique asymptote. All right, so x squared divided by x is x. So we have x squared, and then we're going to subtract, and that cancels. So then we bring down the next term, 0x divided by x is 0. So multiply that by x, subtract, and then bring down the next term, which is 4. And, negative 4. Negative 4 divided by x, there is no expression. So negative 4 is our remainder. R of x. And x plus 0, which just simplifies to x, is our quotient. Okay, so the equation for the oblique asymptote is going to be y equals x. Okay, y equals x. Now, we also want to know if there is a point that lies on this asymptote. Okay, so is there an x value that gets us the y x? So to do that, we're going to set r of x. So that's the x squared minus 4 divided by x. We're going to set it to x, which is the oblique asymptote, and we're going to now solve for x. So we'll multiply x on both sides, so x squared minus 4 equals x squared. We'll subtract x squared to the right-hand side, so that's negative 4 equals 0. So we know negative 4 does not equal 0. Therefore, the graph doesn't intersect y equals x. Okay. Alrighty. So now we have a lot of our key information. So we can now use the real zeros of the numerator and denominator to divide our x-axis into intervals so we can find additional points to plot on our graph. So the real zeros of our numerator and denominator are the -2, 0, and 2, which makes 4 intervals. So we have -infinity to -2, -2 to 0, 0 to 2, and 2 to infinity. Okay, so now we're going to choose a value in each interval. So I'm going to choose -4, -1, 1, and 4. I'm then going to evaluate r at each of these chosen numbers. Okay, we should be able to substitute these values in, and we can use our calculator to help us as well. Okay, so let's plug in our equation. So I'm going to clear that and enter in our equation. So we have x squared minus 4 divided by x. And I want to go to the table. So I'm going to need -4, -1, 1, and 4. So I have -4, -1, 1, and 4 right here. Notice that 0 was eliminated from our domain, and our calculator confirms that. All right, because we have a vertical asymptote when x equals 0. So that was nice to see that our calculation for that was correct. All right, so now we have our points. So we have -3, 3, -3, and 3. So this y value is now the y coordinate of the point -4, -3. Since -3 is negative, the location of this point is going to be below the x-axis. Our next point is -1, 3. Since 3 is positive, it's going to be above the x-axis. I forgot to include x-axis. Our next point is 1, -3. Since the y is negative, it's going to be below the x-axis. And our fourth point is 4, 3. So this is going to be above, since 3 is positive. Okay, nice. Well, now that we have 4 additional points, we can now graph our function. So we know that we have a vertical asymptote when x equals 0. So when x equals 0, that is equivalent to the y-axis. We also have an oblique asymptote, y equals x, which is a diagonal line here that looks like this. Okay, so that's y equals x. To help you plot that, just plug in values. So if I plug in 1, I get 1. Plug in 2, I get 2. And then create your dashed line from there. All right. So I also know I have 2 x-intercepts, and that is 2, 0, and -2, 0. I don't have any y-intercepts, and I have no values that intersect my oblique asymptote. Okay. Now I'm going to plot my additional points that I just found. So the first one was -4, -3. Then I had -1, 3. Then I had 1, -3. And then I had 4, 3. Okay. So now we can draw our lines. Okay, let me draw that one again. I think I can do a better line. There we go. Okay. There we go. All right. Okay. And so now that we have our graph, we can check it on the calculator. We already have our equation in the calculator. So all we need to do is set our window to match. And our window does match. This is similar to our other problem where we extended it to -6 just so that we could see the graph a little better, and 6 on the x and y axis, and we're going by a scale of 1. So we're going to keep that the same, and then we're going to press graph. And you see here that we have a graph that's similar to the one that we have created. Alrighty. Awesome. Okay, next we are asked to graph this rational function x to the fourth plus 4 divided by x squared, going through the same 7 steps that we did in our last problem. All right, so step number 1, we're going to factor the numerator and denominator and then also find our domain. Okay, so r of x equals x to the fourth plus 4 divided by x squared. This cannot be factored, so this is the factored form. And our domain, we would set our denominator equal to 0. So then x is going to equal 0. So our domain is going to be all x values except for when x equals 0. Okay. Number 2, we want to write r in lowest terms. There are no common factors in the numerator and denominator. So r of x is in lowest terms. Okay. Then for step number 3, we want to find the y and x intercepts. Okay. We know for the y-intercept, we are going to substitute 0 for x. Since x cannot equal 0, there is no y-intercept. Intercepts because x cannot equal 0. Okay, so now we'll find the x-intercepts, and this is setting your r of x equal to 0. Okay, so when we take our numerator and set it equal to 0, solve for x, we take the square root, we'll get plus or minus 2i. Okay, so we have imaginary numbers as our zeros. We want real numbers. So since x squared plus 4 has no real solutions, there are no x-intercepts. So no x-intercepts since x squared plus 4 has no real solutions because we got imaginary numbers. All right, so those are our first 2 steps, or first 3 steps. Now let's go find our asymptotes. So for step number 4, we find our vertical asymptote, and our vertical asymptote is the 0 of our denominator. So we already know the 0 of our denominator because we found it when we looked at our domain. So our vertical asymptote is going to be x equals 0. And remember, we found that by setting x squared equal to 0 and solving for x. Okay, so that's our vertical asymptote. Now, since this factor, or the factor that got us our vertical asymptote, has a multiplicity that is even, so multiplicity is even, the graph approaches either infinity or negative infinity on both sides of the asymptote. Asymptote. All right. So we found a vertical asymptote. So now let's determine if we have a horizontal or oblique. So this is step number 5. Okay. So P of X, the degree is 4. Q of X, the degree is 2. So N equals 4, M equals 2. Okay. So our expression is going to be N is greater than or equal to M plus 2. N is 4, M is 2. Okay. Now when we have this expression, we know that our asymptote is going to be the ratio of the leading coefficients of our numerator and denominator times x to the power n minus m. Okay, so if we substitute in our values, we would have 1 divided by 1 times x to the power 4 minus 2, which gets us x squared. Okay, so for our asymptote does not equal this. It actually resembles it. My apologies. When n is greater than or equal to m plus 2, we actually do not have a horizontal or oblique asymptote. However, our graph is going to resemble a certain graph. And the graph in this case that our function r of x resembles is going to be the graph y equals x squared. So we have no horizontal asymptote or oblique asymptote. However, our graph resembles y equals x squared. Okay. Since we have no asymptotes, there's no points to find that lie on the horizontal or oblique asymptote. So we can go straight to step number 6. So our real zeros in our numerator and denominator are just going to be 0 because the zeros of the numerator are not real solutions. So 0 is our only real zero. So we only have 2 intervals, negative infinity to 0 and 0 to infinity. So we can choose a value on either side. I will choose negative 2 and 2. So we're going to substitute in negative 2 and 2 into r and find the y. So let's go grab our calculator. All right, and we're going to substitute in our new r of x, which is x to the 4th plus 4 divided by x squared. Enter that in. We'll go second table. I want the values of negative 2, which is 5, and 2, which is also 5. So I have 5 and 5. So my 2 points are negative 2 and 5 and 2 and 5. Both of them have a positive value, so both points are going to be above the x-axis. Alrighty. But I know that my graph is going to resemble y equals x squared. Alrighty. Okay, so let's graph. So we know that we have no y-intercepts. We also have no x-intercepts. So we won't need to plot any of those points. We do have a vertical asymptote, and that's when x equals 0. So when x equals 0, it's another way of saying the y-axis. Okay. We have no oblique or horizontal asymptote, but we know our graph resembles y equals x squared. So let's just plot that graph. Alrighty, let's see. Let's make it a little wider. There we go. So I'm just going to do a rough sketch here of a parabola. Okay, so it's going to resemble y equals x squared. Okay, so now I'm going to plot some points. So I have the 2 points that I found, which was -2, 5, -2, 5, and 2, 5. Okay, and you notice here I don't really have any other points. So let's go back to our calculator and grab some. Okay, so I have 1 and 5, 2 and 5 as well. And then I have some really small or larger numbers as well. But they're written as fractions, which is totally fine. All right, so I kind of now want a visual of what this potentially could look like so that I can draw my graph. So let's go to window and set up our window to match what we have here in our notes. So our min here is -3, max is 3. It's going by a scale of 1. Our y min is -2. Our y max is 12. And it's also going by, not by a scale of 1. Actually, it's going by 2. All right. And so now we're going to press graph. Okay, so our graph is going to look similar to this. All right, so we had 1, 5, and -1, 5 as well. So we'll look something like this. Alrighty. And it's just a rough sketch. Excellent. Okay. Let's do another one. So now we're asked to graph this function. R of x equals 2x squared minus 2x divided by x squared plus x minus 6. So we'll go through all 7 steps. So for step number 1, remember we are going to factor r of x and find our domain. So r of x is factorable. So let me write our function first. Okay. In the numerator, I can factor out a 2x, which leaves me with x minus 1. In the denominator, our quadratic can be factored into x plus 3 times x minus 2. So to find the domain, we're going to set our denominator equal to 0. So x plus 3 and x minus 2 equals 0. So x can equal -3 and x can equal 2. So our domain is going to be all x values except for when x equals -3 and x equals 2. Alrighty. Step number 2, we want to write r of x in lowest terms. The numerator and denominator do not have any common factors. So r of x is in lowest terms. Okay. Then for step 3, we're going to now find our y-intercept. To find y-intercepts, we substitute 0 for x. Okay. When we substitute 0 for x, we are going to get 0 in for x. So let's do that. Let me do it over here. So we have 2 times 0 squared minus 2 times 0 divided by 0 squared plus 0 minus 6. So we'll have 0 over -6, which just equals 0. So we'll have the point 0, 0 as our y-intercept. For our x-intercepts, we're going to set r of x equal to 0. Or in other words, we're going to take our numerator, let's take the factored form, and set it equal to 0. So each factor we can now set equal to 0 and solve for x. So we have x equals 0 and x equals 1, which gives us 2 x-intercepts, 0, 0, and 1, 0. Okay, so we have a y and we have 2 x-intercepts. So now we can find our asymptotes. So let's first find our vertical asymptote. Our vertical asymptote is the real zeros of the denominator, which we have already found by factoring the denominator and setting each factor equal to 0. So we have x equals -3 and x equals 2 as our 2 vertical asymptotes. Okay. Now, since the multiplicity is odd, the graph approaches infinity on one side and negative infinity on the other. Okay, that's great. Now for step 5, we can determine if we have any horizontal or oblique asymptotes. So P of x has a degree of 2. Q of x, which is the denominator, has a degree of 2. So n equals 2 and m equals 2. So n equals m because 2 equals 2. So this means that we have a horizontal asymptote, and the horizontal asymptote is going to be the ratio of your leading coefficients, which are 2 and 1. which equals 2. So we have a horizontal asymptote when y equals 2. Excellent. So now let's determine if there is a point on our graph that intersects with this asymptote. So to find that point, we're going to set r of x equal to 2 and determine what the x-coordinate would be. So we'll have 2x squared minus 2x divided by x squared plus x minus 6 equals 2. So we'll multiply both sides by x squared plus x minus 6. That's in the denominator. So I would have 2x squared plus 2x minus 12. Now I want to get all of the values that have an x on one side. So I'll subtract the 2x squared to the other side, so that cancels. I'll subtract the 2x to the other side, and that will also cancel. Wait a minute. That should be negative. Like, that shouldn't cancel. So that means there's an error. That should be negative. Now, when I move 2x to the other side, that will be a negative 2x, which would give me a negative 4x and leave negative 12 on the right-hand side. When I divide by negative 4, I get x equals 3. Okay, so that means the graph intersects the line y equals 2 at the point 3, 2. So I know now that I have a point that lies on my asymptote. Okay. Now we can take our zeros. We have negative 3, 0, 1, and 2. And we can find our 4 additional points. So let's find our intervals. So that's negative infinity, negative 3, negative 3 to 0, 0 to 1, 1 to 2, and 2 to infinity. We need to choose a value within each interval. So we can choose negative 4, negative 2, 0.5, 1.5, and 3. So now we want to evaluate r at each of these points. And we can definitely use our calculator to help us. Or you can do it by hand. Either way works. So let's grab our calculator. Okay, we're going to go to y equals, and we're going to enter in our function. So we have 2, I forgot to add the 2 first. 2x squared minus 2x divided by x squared plus x minus 6. All right. Now let's go to table, second graph, and I have some whole numbers, but I also have some decimals. So I need to have my x's go by 0.5. So we'll go second window, and I want my change in the table to go by 0.5. Okay. Now it's going by 0.5, which is great. And so now I can locate my values. So I wanted negative 4. So I'm just going to round my values or my decimals, my y's, to one decimal place. So I have -4, I have -2, then I need 0.5 right here. I have 1.5 right here, and I have 3 right here. Okay, so now we can plot, or not plot yet, but write these y values in our table. So we'll round this to one decimal place. This one was -3. And then this one will round to 0.1, -0.7, and this one was 2. So we'll have our points wherever our y is positive. That point will lie above the x-axis. Wherever our y is negative, that point will lie below the x-axis. All right, so this is above the x-axis. This is below the x-axis. This is above the x-axis. This is below the x-axis. And this is above the x-axis. So in this case, these all alternate. Alrighty, so now that we have some points, we can now graph. So first things first, let's graph our vertical asymptote and our horizontal asymptote. So we have two vertical asymptotes in this problem. We have one at -3. All right. And we have one at 2. Drawing my dashed lines. Okay. Now we also have a horizontal asymptote at y equals 2. Alrighty. Okay. Now we also know at the vertical asymptote that our graph is approaching infinity on one side and then negative infinity on the other. Okay. So let's now plot some points. Well, especially the ones that we already know. So we know we have a point that lies on our horizontal asymptote, and that's the point 3, 2. Okay. We then also know our y-intercepts and our x-intercepts. So we have an intercept at 0, 0, and we have an intercept at 1, 0. Okay. Then we found 5 additional points. So we had -4 and then 6.7. -4, 6.7. So that's all the way up here. So this is going by 2's. So 6.7 would be like somewhere here. Okay. Then we had -2, -3. -2, -3. So that's 4. So halfway. Then we had 0.5, 0.1. So 0.5. So this is 1. So it's going to be very small. And then we have 1.5 and -0.5. So 1.5, -0.5, 0.7, sorry. So that's almost at 1. Okay. And then we had 3, 2. 3, 2, which we already had. So let's go find in our calculator the point for 4 All right, let's find the point 4, just so that we can, kind of have a better accurate representation of the graph on this side of our vertical asymptote. This one I know kind of goes up like this and comes down. Okay, so that one I understand. And then let's get one over here too in this section as well. So let's see, maybe we can get a -5 just to kind of get an estimate of where that would be. All right, so we want a 4. Let's go see what that is. So 1.7, all right, for 4. So 1.7 would be somewhere around here. Okay. And then we want just a -5 just to get an estimate. So 4.3. So if we were right here, 4.3. So it'll be somewhere right here. All right. So now we can kind of draw a rough sketch of what we believe our graph would look like. Okay. All right. And then this one. Okay. All right. Now let's look at our graph, excuse me, to determine whether our graph looks similar. So let's go to our window and make sure everything aligns. So our x-min, we actually plotted -5. Our, excuse me, our max is, let's go to 5 as well. Scale of 1. Our y-min is -6. Our max is 8. Our y-axis is going by a scale of 2. Okay. All right, so let's press graph. Okay, that is similar. That is very, very similar. Nice. I like. All right. Okay. So now we're asked to graph this rational function, 2x squared minus 5x minus 3 divided by x squared minus 9. So for step number 1, we are going to factor r of x. So we have 2x squared minus 5x minus 3 divided by x squared minus 9. So the numerator can be factored into 2x plus 1 times x minus 3. And the denominator can also be factored. It's a difference of squares. So we have x minus 3 times x plus 3. So to find our domain, we're going to set our denominator equal to 0. So we'll set each factor equal to 0 and solve for x. So we have x equals 3 and x equals -3. So the domain is going to be all x values except for when x equals 3 and x equals -3. Okay. Step number 2, we want to write r of x in lowest terms. So if we look at the factored form of r of x, we'll see that we have a common factor in the numerator and denominator. So when we cancel those common factors, the lowest term of r of x is going to be 2x plus 1 divided by x plus 3. Okay. So this is now going to be the function that we're going to use to evaluate our intercepts and our asymptotes. Okay. So let's find our intercepts. So to find the y-intercept, we're going to evaluate r of x at 0. Okay, so I'm going to substitute in 0. So I'll have 2 times 0 plus 1 divided by 0 plus 3. Okay, and that simplifies to 1 over 3. So I have an y-intercept at 0, 1/3. For my x-intercept, I'm going to set r of x equal to 0. In setting r of x equal to 0, I then set my numerator to 0 and solve for x. So I have 2x equals -1. So x equals -1/2, which gives me the x-intercept -1/2, 0. So I now have one y-intercept and one x-intercept. So the next part is to find our asymptotes. So for step number 4, our vertical asymptote is going to be the real 0 of our denominator. So when we simplify r of x, we got 2x plus 1 divided by x plus 3. So setting our denominator equal to 0, we get x equals -3. So our vertical asymptote is going to be the line x equals -3. All right. Since the multiplicity of this point, the multiplicity of the factor that got us this line is odd. So the multiplicity is odd. The graph approaches infinity on one side and negative infinity on the other. Okay. Now, what about our other factor that we eliminated, common factor? So when x equals 3, there is a hole. Now, where is the hole? Well, we are going to substitute in 3 into our lowest term or reduced form of r of x. And we'll get 2 times 3 plus 1 divided by 3 plus 3. That equals 7 over 6, which is roughly 1.167. So when x equals 3, there is a hole at the point 3, 1.2. Okay, so since 3 is not in the domain and x equals 3 is not a vertical asymptote, we have a hole. All right. So when you eliminate a common factor, when you reduce your rational function, that should signify to you that you have a hole in your graph. All right, so now let's see if we have a horizontal or oblique asymptote. So P of x, our degree is 2. Q of x, our degree is also 2. So n equals 2, m equals 2, so n equals m, because 2 equals 2. So that means our graph has a horizontal asymptote, and that line is going to be the ratio of our leading coefficients. So that's going to be 2 and 1. So that's going to be 2. So our horizontal asymptote is going to be the line y equals 2, which is great. So now we need to determine if our graph intersects this asymptote at a point. So we're going to set r of x equal to 2. So we'll have 2x plus 1 divided by x plus 3 set equal to 2. So we'll multiply both sides by x plus 3, similar to what we did on the last problem. So we'll have 2x plus 6 equals 2x plus 1. So the two x's are going to cancel and we'll get 6 equals 1, which is not true. So the graph then doesn't intersect the line y equals 2. Okay, so let's write that down. The graph doesn't intersect y equals 2. Okay. All right, so now we found all of our vertical asymptotes. We've identified our hole. So now we can find our additional points. So we have 3 real zeros, -3, -1/2, and 3. Okay. And so our 4 intervals are -infinity to -3, -3 to 1/2, -1/2 to 3, and 3 to infinity. The numbers I have chosen are -4, -2, 2, and 7. So I'm going to evaluate r at each of these 4 points. So let's set that up. Okay. And now I'm going to grab my calculator, go to y equals, and I'm going to enter in my equation. All right, so I have 2x squared minus 5x minus 3 divided by x squared minus 9. Okay. Now I'm going to go to my table. Okay. And I want -4. I want -2. I want 2. Let's go down and see what that value is. I want 2 and I want 7. And that's 1.5. Okay. All right. So let's jot that down in our notes. So 1.5, 1, -3, and 7. So that gives us the points -4, 7, -2, -3, 2, 1, and 7, 1.5. So if our y is positive, we are above the x-axis. So both of these are going to be above the x-axis. Oh, and the last one as well. Cool. And then our point -2, -3 is below the x-axis. Okay. So now we can move on to our step number 7. which is to graph. So let's first plot our asymptotes. So we have an asymptote, a vertical asymptote at x equals -3. So -3, this goes by 2, so right here. So -3, let's draw that dashed line. So that's x equals -3. And we have a vertical asymptote at y equals 2. Okay. And we have our intercepts. We have 0 and 1/3. 0 and 1/3. So that's 0.33. Okay. 0 and 1/3. So that's 1. So 1/3 will be right here. Okay. Then we also have an x-intercept at -1/2, 0. So that's 1, -1/2, 0. So right there. Okay. We also have a hole. That was also a point that we found. And our hole is at the point 3, 1.2. So 1, 2, 3. And 1.2. So we have a hole. Okay. And then we have our 4 points that we found in step number 6. So we have -4, 7. So up here. We have -2, -3. We have 2, 1. And we have 7, 1.5. And 7 is way off of our board. So we're unable to plot that point. Okay. Alrighty. So we can now connect our dots. So this is going to look something like this. And this one will look something like this. Alrighty, that's so cool. There's a hole in our graph. Now let's check this with our calculator. Okay, let's make sure our windows match. So our min, okay, we did to -5. 5, scale goes by 1. Y min is -6, max is A, and it's going by 2. Great. Let's press graph. Ooh, yay! I see it. Great. All right, so our graph here, our calculator here, does not represent our hole. All right, but we know that there is a hole at that point because of our common factor. Great. Awesome. So now for this example, we are going to work backwards. So we're now actually going to construct a rational function from this graph. Okay, so using the steps that we went through, we're going to kind of think about how would that be represented on the graph. And then from there, identify our factors, which will allow us to find our rational expression. Okay, so let's first state everything that we know in this graph. Okay, well, we have a horizontal asymptote right here, and that's y equals 1. Okay, so this is a horizontal asymptote. Okay, since we have a horizontal asymptote, we know that n is going to equal m. Okay, so that means our powers in the numerator, or our degree in the numerator and denominator, is going to be the same because y equals 1. Okay. Now we have 2 vertical asymptotes. Okay. So we know then that our domain is not going to include x equals -4 and x equals 2. Okay. We have an x-intercept right here. We have an x-intercept. We know this x-intercept is going to have a multiplicity that is even, and we know it's going to be even because it touches the x-axis. We also have an x-intercept right here, and this multiplicity is going to be odd because it crosses the x-axis. Okay. Now at our vertical asymptotes on the left side here, so from the left, let me write that. From the left, we are approaching infinity, and then from the right, we are approaching negative infinity. Since we are approaching opposite directions, we know we're going to have an odd multiplicity on the factor that gave us this VA, vertical asymptote. For the other one, we are approaching negative infinity and negative infinity, so the same direction. So this is going to be an even multiplicity. So the factor that gave us this VA is going to have an even multiplicity. Okay. Alrighty. We also have a y-intercept right here. That's something to note. And let's see. No slant. I think that's it. All right. So we know r of x is going to be in the form p of x divided by q of x. Okay. Now, for our numerator, okay, so for our p of x, okay, we want it in lowest terms, okay, and we know that our numerator determines our x-intercepts. So for p of x, we want the factor form of our x-intercepts. So our x-intercepts are -1 and 3. -1 and 3. So the factored form would be x plus 1 and x minus 3. Okay. Now, the x-intercept, -1, is even. So let's give that a power 2. And the x-intercept 3 is odd. So that would have a power of 1. Okay. Now for q of x, okay, this is a denominator, and we want it, of course, in lowest terms. And this determines the vertical asymptote. So that's, we set the denominator equal to 0 to find the vertical asymptotes. So we have a vertical asymptote when x equals -4 and x equals 2. So the factors would be x plus 4 and x minus 2. Since the vertical asymptote x minus 4 has an odd multiplicity, we'll just give that a power 1. And the vertical asymptote x equals 2 has an even multiplicity, we'll give that 2. Okay. Now we know from the horizontal asymptote that the degree of the numerator and the degree of the denominator must equal each other. So the total power in our numerator, the degree is 3, and the degree of our denominator is also 3. Okay, so the leading coefficients for both of these are going to be the same. So we know then that r of x equals x plus 1 squared x minus 3 divided by x plus 4 times x minus 2 squared. And that is our rational function for this graph. Okay. So we know our function. Feel free to multiply that all the way through if you like, but we're just going to keep it in factored form for now. But that is how you can use information provided to you on the graph in order to find your rational function. Awesome. Alrighty. So now we're going to go to objective number 2. Solve applied problems involving rational functions. So for this example, finding the least cost of a can. So Reynolds Metal Company manufactures aluminum cans in the shape of a cylinder with a capacity of 650 cubic centimeters. The top and bottom of the can are made of a special aluminum alloy that costs 6 cents per square centimeter. The sides of the can are made of material that costs 3 cents per square centimeter. A is asking us to express the cost of material for the can as a function of the radius r of the can. Okay. So the first thing that we need to do in order to find our expression is to note that the material that they're using consists of 2 different types of shapes. We have 2 circles and we have 1 rectangle. So C is going to be the cost of the top and bottom, which are the circles, plus the cost of the sides of the side. So the top and the bottom are circles. So we'll have 2 times its area, which is pi r squared, okay, times its rate. And so in our problem, it says the top and the bottom are made of a special aluminum that costs 6 cents per square centimeter. So that's area because it's squared. So we'll multiply this by our 6 cents. So that's the cost of the top and the bottom. So the cost of the side is going to be its area times the side. So the sides of the can cost 3 cents per square centimeter. So we'll multiply that by 3 cents. Okay. So in simplifying, the cost equals 0.12 pi r squared plus 0.06 pi r times h. That's the cost of the material. Okay. But we're not done because our problem also says that there is a capacity. So the cylinder, the shape of the cylinder has a capacity of 650 cubic centimeters. So that's volume. Okay. So there's an additional restriction on H and R. So the volume of the can cannot exceed 650. Okay. So let's find out how to do that one. So our costs, let me rewrite that here. It's pi r squared plus 0.06 pi r h. Volume is equal to pi r squared h. Okay. And the maximum volume is 650. Okay. So we want h in terms of r. So we will divide both sides by pi r squared in order to get h by itself. So h equals 650 divided by pi r squared. Okay, so now substituting that in for h into our cost formula, we have 0.12 pi r squared plus 0.06 pi r times 650 divided by pi r squared. Okay, we can simplify this some more. I get 0.12 pi r squared. The pi's cancel, r's cancel, and then 0.06 times 650 equals 39 over r. Okay, so we would multiply this term by r in the numerator and denominator, which gives us a cost equation of 0.12 pi r cubed plus 39 divided by r. Okay, so this is going to be the cost of making our cans. Alrighty. So for B, we want to use our graphing calculator to graph this function. So we're going to use the calculator to graph C. Let's note here that R, all right, R is going to have to be positive. It's going to have to be greater than 0 because you can't have a negative radius. Okay, so our domain is going to be all values of R where R is greater than 0. Okay, it can't even equal 0 because then the can wouldn't actually exist. So let's pull out our calculator. Okay, and I'm going to just move it over here. We'll go to y equals, and we'll enter in our equation 0.12 pi, so that's second caret, r squared, so that's x, cubed. So we'll go here to math, plus 39 divided by x. We're going to enter in our equation, so we'll press enter. All right, so now we're going to go to Zoom, and we want to fit our equation onto our screen. So we'll go to Zoom Fit, which is 0. And we see this lovely curve. Okay, so it fit everything onto our screen. Great. So now that we have everything on our screen, we can now go to our next problem. But before we do, note that R is greater than 0, so everything is in the first quadrant on our screen here. All right. So C is telling us, or asking us, what value of R will result in the least cost? So what value of R? So we're trying to find R, or in other words, on our calculator, the lowest value of X. And then D is related to that. It's asking what is the least cost? Well, the least value of R should give us the least cost. So we're trying to find the minimum. If we can find the minimum point, then the X coordinate will give us the least value of R, and the Y coordinate would give us the least cost. So let's find that. So in our calculator, we are going to use the minimum button to help us find it, just so that I can see where the minimum will be located, I'm going to provide my y-axis some negative values. So I'm going to change my window so that my y-min is negative 100. All right, so now when I graph it, I can kind of see more clearly where my minimum will be located. Okay, so we're going to go to calc, which is right above trace. So that's second trace. And we'll go to number 3, which is the minimum. And we now need to identify the left bound of where our minimum is located. So I'm going to move this cursor just so that I can kind of locate where that minimum value might be. So, I'm getting lower here. So, and then I'm going up. All right. So my minimum value is around 3.7, 3.8. So I'm going to do a number on my left bound. So we'll do 3.6 and I'll press enter. My right bound, I'll go to 3.9, enter. And then I'm going to try and guess. So it's probably going to be around here, 3.8. And the calculator then makes a more educated guess for me. So the minimum value is the point 3.73 and the y coordinate 15.7. Okay, so to answer our question then, all right, the cost is least for a radius of 3.73. Okay, and that's for R, and R is in centimeters. Okay, now what is the least cost? Well, when C is 3.73, well, more specifically, when we evaluate C at 3.73, we get 15.70. Okay, so the cost would be $15.70. So this is the least cost. The least cost is, alrighty, great. And that concludes section 3.6.